So it's a great pleasure to welcome Miguel Domínguez Vázquez from Universidade de Santiago de Compostela, speaking on cohomogeneity one-actions on symmetric spaces of non-compact type.
So thank you for the introduction, and thank you very much for the invitation. It's for me a pleasure to give a talk in this so popular seminar. So I would like to tell you about an ongoing joint work with Jose Carlos Díaz-Ramos and Tomás, our PhD student, Tomás Otero, all of us from the University of Santiago de Compostela in Galicia, Spain. And the goal of this work is to provide new tools for the classification problem of cohomogeneity one-actions on symmetric spaces of non-compact type, and in particular to get classifications in symmetric spaces of higher rank, of rank higher than 2. We are concluding the paper, and hopefully it will be on the archive soon in the next few weeks. So let me start by quickly recalling what a cohomogeneity one action is. So for the moment, let M be a Riemannian manifold, and if I have connected Lie group acting by isometries on M and properly, then such action is said to be of cohomogeneity 1 if it has an orbit that is a hypersurface, or equivalently, if the lowest codimension of the orbits is 1. So many things are known for cohomogeneity one actions. The orbit space is, of course, one-dimensional. There can be at most 2 singular orbits, and the remaining orbits are regular, are hypersurfaces. Let me simply show here 3 very easy examples of cohomogeneity one actions on the Euclidean 3 space. The first one, the action of SO3 by rotations that has a fixed point, exactly 1 singular orbit. The other orbits are principal. Then you have this action of R2 by translations. In this case, you don't have any singular orbit. You can mix rotations and translations to get this singular foliation by cylinders and their common axis. In some of these actions, there might be other groups acting with the same orbits. But I'm interested not in describing all the groups that act with cohomogeneity 1, but in understanding the orbit foliations of cohomogeneity 1 actions. In other words, what I'm interested in is to classify cohomogeneity 1 actions up to orbit equivalence. I want to consider 2 actions to be orbit equivalent if they have the same orbits, or more precisely, if there is an isometry of the ambient space that maps orbits of one action to orbits of other action. So of course, cohomogeneity one actions have been used to construct examples of manifolds and submanifolds with special geometric properties, and this equivariant method has been very successful. But the problem I'm interested in is different. It's fixed, given a fixed Riemannian manifold with a large isometry group, classify the cohomogeneity one actions on such manifold up to orbit equivalence. So this is a classical problem, and it's interested from the viewpoint of Riemannian submanifold geometry. If you want to develop a theory of submanifolds in spaces where you have many isometries, one of the first steps, natural steps, is to address the study of homogeneous hypersurfaces. This means the regular orbits of cohomogeneity one actions. Okay. As I said, this is a classical problem. It goes back at least to the works of Levi, Civita, Segre, and Elie Cartan in the 30s. in their study of the so-called isoparametric hypersurfaces, which are more general objects than homogeneous hypersurfaces. So from their classifications in Euclidean and hyperbolic spaces, one can get the classification of homogeneity one actions up to orbit equivalence on these spaces. We also have a classification of these actions on round spheres due to Xiang and Lawson and Takagi and Takahashi, also for the other crosses, for the other compact rank 1 symmetric spaces, and more generally for the irreducible symmetric spaces of compact type. This is a classification due to Andreas Kollross. I remark here that we don't know a classification for reducible symmetric spaces of compact type. So the problem I'm interested in is what happens with homogeneity one actions on symmetric spaces of non-compact type. So the dual spaces to the symmetric spaces of compact type. So let me start with the simplest example of symmetric space of non-compact type, namely the real hyperbolic plane. Okay. Let us regard it in the half plane model. Okay, and we know that the Lie group G SL2R acts on this half plane by Möbius transformations in this way. Okay, this action is transitive, and if you consider the standard hyperbolic metric, then it is an isometric action. Okay, we can compute the stabilizer at some base point, say the imaginary unit. And then it's easy to see that it is the group SO2. So you have this description of the hyperbolic plane as a homogeneous space. Indeed, this is a symmetric pair, SL2R over SO2. Okay, I will consider two more groups, one-dimensional groups. The first one is A, is this group of diagonal matrices. And the second one is this N, this group of upper triangular matrices with ones on the diagonal. Okay, these three groups, K, A, and N, are important because they appear in the Iwasawa decomposition result, which we will see later in the more general setting of symmetric spaces of non-compact type. But we can get a picture of how these groups act on the hyperbolic plane. Here you have the representation of their orbit foliations. In the case of K, you have a fixed point, the imaginary unit, and the other orbits are geodesic spheres, in this case of dimension 1, that fill the whole space. In the case of A, you have a geodesic, this vertical line in here, and the other orbits are equidistant or parallel curves to this geodesic. And in the case of N, you get a horosphere foliation. Each orbit is a horosphere with a common point at infinity. And it's not very difficult to show that in this ambient manifold, the homogeneity one actions are up to orbit equivalence, one of these three actions. Okay, as we will see in the general case for other symmetric space of non-compact type, this gets much more involved. Okay, before stating our main result and giving you the ideas, the main ideas behind the proof, I would like to present here some previous work on this topic. Okay, so there are several papers that directly or indirectly are related to this problem. The case of spaces of rank 1, namely the hyperbolic spaces over the distinct norm division algebras, this is nowadays completely solved. In the real case, this was addressed by Cartan in his study of isoparametric hypersurfaces. And then in the general setting by Berndt and Tamaru, who classified the complex and Cayley cases, and jointly with our student Alberto Rodriguez Vázquez, we completed the classification in the quaternionic setting a couple of years ago. Okay. In these spaces, symmetric space of non-compact type of arbitrary rank, since they are Hadamard manifolds, homogeneity one action cannot have two singular orbits. So you have two possibilities: no singular orbit or one singular orbit. the case where all orbits are regular is already completed. Okay, so we have a complete classification in here. So one singular orbit. The particular case when this singular orbit is totally geodesic is also known. Okay, it's due in to Berndt and Tamaru in a different paper. And I would like to remark here that this paper is the only one, under the assumption that you have a totally geodesic singular orbit, this is the only assumption where the only case where you can use duality of symmetric spaces to appeal to Kohlross's classification in the compact setting. Otherwise, it's not possible to use the duality of symmetric spaces to get classifications. Okay, but anyway, under this assumption, we have a complete list. So what we know in the general setting without any restrictions. So the most important paper here is this one by Berndt and Tamaru, who provided, let's say, a list of possibilities on how to construct all possible actions, all possible cohomogeneity one actions. And in particular, they introduced two new methods, which I will mention later. Okay. Then these methods were revisited in these other two papers, and as a consequence of all these results, we have, apart from the classification in the rank 1 symmetric spaces, also classifications in these rank 2 symmetric spaces. This is not the whole list of rank 2 spaces, but just some of them. Okay. But we don't know any complete classification in any space of rank 3, 4, or higher. Okay, and this is one of the issues we wanted to address. Okay, so I state here our main result, which says the following: a cohomogeneity one action on a symmetric space of non-compact type is orbit equivalent to one of the following 5 possibilities. Okay. We can distinguish two big cases, let's say, when you don't have any singular orbit or when you have one singular orbit. And the first case, you have these two possibilities, solvable type or spherical type. I will explain this later. And when you have a singular orbit, you get 3 ways to construct such cohomogeneity one actions. Okay, they involve these 2 methods that I mentioned before: canonical extension and idempotent construction, that were initially introduced by Berndt and Tamaru. Okay, I will explain later what all this means. Okay, but I just wanted to give you an idea of what our main theorem says. And at the end of the talk, I will try to tell you how we can apply this result to get a classification in this family of symmetric spaces. The spaces SLNR over SON. Okay, so this is a family that includes all ranks. So in particular, this gives first classifications in rank higher than 2. And we also get a result that allows us to reduce the classification problem on a reducible symmetric space to understanding the actions on each one of the irreducible factors of such reducible symmetric space. Good. So let me fix some notation. So one of the problems of this work is that it requires a lot of notation. I will try to keep this to a minimum, but I also want it to be informative. If you get lost with the notation at some point, don't worry. I still think that you can grasp some main ideas of the proof. Okay, so as above, let M be a symmetric space of non-compact type, and we know it admits a coset description as a homogeneous space G mod K, where G can be taken as the identity component of the full isometry group of N, and K is the isotropy in G of some base point, which is arbitrary, but we fix from now on. Okay, O is an arbitrary point in N. Good. So we know that a symmetric space of non-compact type is a Hadamard manifold, so non-positive sectional curvature. It's diffeomorphic to an open Euclidean ball. So you can have in mind this picture of such a space as an open Euclidean ball with some metric with very nice properties, a symmetric metric with lots of isometries and so on. Okay. G, the Lie algebra of the isometric group, is real semi-simple. K is compact. Okay. Now we will consider several decompositions that play an important role. The first one, simplest one, the Cartan decomposition. In G, you take the orthogonal complement of K with respect to the Killing form of G. Okay, this is P. I call it P, and P is naturally identified with the tangent space at the base point. Now, on G, you modify the Killing form, BG, by changing its sign on K. Okay, and then this becomes an inner product, a positive definite inner product on G. We will be using this inner product implicitly in the rest of the talk. Okay, now we consider a maximal abelian subspace of P. All such subspaces have the same dimension, which is, by definition, the rank of the space, of the symmetric space. If you exponentiate these subspaces, when you get the maximal flats, okay, the maximal totally geodesic and flat submanifolds of M. Okay, now if you consider this family of endomorphisms of G, okay, do the bracket with elements of in A, these endomorphisms are self-adjoint with respect to the inner product, and they commute to each other. Okay, so they diagonalize simultaneously. So there is a common eigenspace decomposition of G, and this is the so-called restricted root space decomposition. Okay, which says that G splits as a direct sum of some subspaces, G naught and G lambda, and these G lambda are parametrized by some elements in this set, finite set, capital delta, and this is the set of restricted roots. Okay, formally these are covectors in A. Okay, in this maximal abelian subspace of P. Okay, this is the set of roots. I will forget about the word restrictive throughout the talk. Okay, this set of roots is a finite subset of A star that form a root system. So this means that it has some nice symmetry properties. In particular, whenever you have a root, a vector in this capital delta, then the opposite vector is also in a root. Okay, so you can consider the a set of positive roots and a set of negative roots. Let's see how to do it through an example. Here I'm considering a root system of non-reduced type. This means that we have some roots here, for instance, this one here, that admit a double root. Okay, so this root system does not appear in the classification of compact groups or in the classification of complex semi-simple Lie groups. You must go to the theory of real semi-simple Lie groups or symmetric spaces. Okay, so in order to define positive roots, we take a hyperplane not containing any of the roots, and we choose one of the half spaces, half planes. Okay, so the roots on the one side are precisely the positive roots, and the others are the negative roots. Okay, among the positive roots, there are some roots, some elements that are not sum of several positive roots, and these are called the simple roots. In this case, I call them alpha 1 and alpha 2, these two roots here. Okay, so it turns out that any positive root is a linear combination of these simple roots with integer coefficients. Okay, of course, the simple roots form a basis of this vector space. Okay, and therefore the cardinality of pi, the set of simple roots, is the rank of M. Okay, which was the dimension of the vector space. Okay, with the simple roots, one can construct the Dinkin diagram, which in this case has this form here, and here you have a double node corresponding to the root alpha 1 and its double to alpha 1. Okay, good. So now that we have the positive roots, I'm going to consider a subalgebra of G associated to the set of positive roots. This will be N. It's a nilpotent Lie subalgebra of G. Okay, so we add all the root spaces corresponding to positive roots. Okay, So we have here the Lie algebra K, the isotropy Lie algebra, A, which was an abelian subspace in P, and this N. Okay, and this gives us the Iwasawa decomposition of G. Okay, it's a vector direct sum. So these are not ideals. And at the Lie group level, G is diffeomorphic to the product of K and the connected subgroups with Lie algebras A and N. Okay. So A plus N is a Lie subalgebra of G. It's a semi-direct sum. And you can consider the connected subgroup of G, A, N, with such Lie algebra. Okay, so you can imagine that G mod K is M, so G mod K should be identified with A times N. Okay, so you can formalize this. M turns out to be diffeomorphic to this solvable Lie group AN. And if you pull back the metric, the symmetric metric on M to this Lie group, it turns out to be a left invariant metric. So this means at the end of the day that any symmetric space of non-compact type is isometric to a particular solvable Lie group with a left invariant metric. Okay, so this can be helpful to construct examples of submanifolds by constructing examples of subgroups, and this is a purely algebraic problem. So this helps a lot in this setting. Good. As an example, well, throughout the talk, I will be using a picture that I would like to explain now in order to help you to follow a bit better the discussion. So here I consider this symmetric space SL8R over SO8, which has rank 7. So its Dinkin diagram is this one. Okay, so each one of the nodes corresponds to a simple root, okay, to the elements of pi. Now we can consider here some nodes so that they represent all the positive roots. Okay, so here we have all the positive roots. For instance, this node here is the positive root that is the sum of the 3 simple roots on the basis of the triangle, alpha 4, 5, and 6 in this case. Okay. Good. We can also plot here the negative roots, something as in here. Okay. And if we want okay, and this represent all the roots. Good. But we can also use this picture to regard the subalgebras of G. For instance, we can regard this as N, because N is the sum of the root spaces corresponding to positive roots. You can consider the sum of the root spaces of negative roots. Here, theta is the Cartan involution. And what is left here is G naught. Okay, in this case, G naught is precisely A. So if we want, we can represent this by this rectangle here. Okay, so I will be using this picture in the talk. Okay, so now our problem. We want to analyze homogeneity 1 actions on a symmetric space M of non-compact type. So we consider a connected and closed subgroup of G acting with homogeneity 1 on M. It's assumed to be closed because I'm considering proper actions. Okay, so we distinguish 2 big cases, no singular orbit or 1 singular orbit. So first case, if you don't have any singular orbit, then you get a homogeneous regular foliation. Okay, and you can get examples by considering codimension 1 subgroups of AN. Okay, recall AN is identified with M, so a codimension 1 subgroup gives you a codimension 1 homogeneous regular foliation, a homogeneity 1 action. Okay, so one way to consider such subgroups, you take the I will be expressing here some Lie algebras. Lie algebra H will be in this case considering the whole Lie algebra A plus N and removing something of 1 dimension in A. So in this talk, this symbol here means orthogonal complement, in this case, of this L in A. And L in this case is a 1-dimensional subspace of A. Okay. So this has codimension 1 in A plus N. So the corresponding group, connected subgroup of AN, acts with homogeneity 1 and without singular orbits. Another example. you remove something of one-dimensional from n, but n is graded, so you cannot remove anything. You cannot remove whatever you want. You have to remove something from a simple root space. Okay, for instance, something as in here. Okay. So this gives two families of examples, and it was proved by Berndt, Díaz-Ramos and Tamaru that up to orbit equivalent, these are the only examples of homogeneity one actions without singular orbits. Okay, we give a name to these two families of examples. The first one, we say it's of horospherical type. The second one of solvable type. The first one is called of horospherical type because for some choices of L, this gives rise to horosphere foliations. Okay, and this is something different from, very different from the compact setting. Here you have many choices in higher rank. You have many choices for L, so you get uncountably many examples up to orbit equivalence. Okay, so this case is very well understood. So let us move on to the case of one singular orbit. As I said before, there is no possibility for two singular orbits. Okay, so M is not assumed to be irreducible. So let us consider the RAM decomposition of M. So as a product, Riemannian product of M1 up to MS, where each Mi is a symmetric space of a non-compact type. Okay. So these are irreducible factors. The corresponding isometry group has a Lie algebra that is semi-simple, and each simple factor is the Lie algebra G1 and the Lie algebra GS, G1, G2 up to GS. Okay, good. So now what we do is the following. Between G, okay, the whole isometry Lie algebra, and H, the Lie algebra of the group acting with homogeneity 1, we consider in between a maximal proper subalgebra of G containing H. Okay, and by a result of thinking, such a maximal proper subalgebra of G must be of these two types. The type on the right is one of the types you could expect. Q splitting nicely with respect to the composition of G into simple factors. Okay, recall the GIs are the simple factors of G. Okay, and this QL lies in the simple factor GL and it's maximal, a maximal subalgebra there. Okay, the other case is when you consider in Q all the simple factors but two, say with indices J and K, and you add this diagonal Lie subalgebra of Gj plus Gk. How do you construct this? Okay, so first you need the simple factors Gj and Gk to be isomorphic, and you consider an isomorphism. Okay, this means that at the symmetric space level, that the corresponding factors, reducible factors, are homothetic, are isometric up to rescale. Okay, now you consider this diagonal Lie subalgebra, which is canonically isomorphic to Gj and to Gk. Good. This case turns out to be relatively easy. Okay, Q, the connected group with Lie algebra, this maximal Lie subalgebra, turns out to act hyperpolarly for those who know what that means. And importantly, with homogeneity, the rank of Mj or of Mk. But H was contained in Q, and H acted with homogeneity 1. So Q acts with homogeneity, must act with homogeneity 1. Okay, it cannot act transitively. So the rank of Mj and the rank of Mk is 1. This means that these are hyperbolic spaces over some division algebra F. Okay, and we knew that they were homothetic. Okay, and the actions of H and Q are orbit equivalent. So this case is understood. Okay, so the up to orbit equivalence, the actions are those of groups Q with these Lie algebras. Okay, so let's go for the difficult case. Okay, and here we will be considering some subcases. So Q split nicely with respect to decomposition into simple factors of G. And QL is a maximal Lie subalgebra of GL. Good. Now, by a result of Mosteau, this QL is either a maximal reductive subalgebra or a maximal parabolic subalgebra of GL. Okay. So here, by reductive, I not only mean that it is abelian plus semi-simple. I mean something stronger than this. It is a maximal algebraic reductive subalgebra. And in our context, what this means is that QL is invariant under some Cartan involution of GL, of the simple factor GL. Or if you want, it's canonically embedded with respect to a Cartan decomposition of GL. And geometrically speaking, this means that the associated group, capital QL, acts on this factor with a totally geodesic singular orbit, a proper totally geodesic singular orbit. Okay, so in particular, it doesn't act transitively. So H again, so the same happens with Q instead of QL. And so again, H acted with cohomogeneity 1, Q doesn't act transitively, so both actions must be orbit equivalent. Okay, and if you remember, I said before that these actions with totally geodesic singular orbits had been classified using duality of symmetric spaces by Berndt and Tamaru. So here we have a complete list. So this case again is well understood. So we are left with the possibility that H, okay, is contained in a Q as in here, where this factor QL is parabolic. Okay, this is the case we are going to analyze in the rest of the talk. So what does it mean to be parabolic? So a parabolic subalgebra of semi-simple Lie algebra G, geometrically speaking, is the Lie algebra of the stabilizer in G of a point at infinity of the symmetric space. Okay, so remember, we have a symmetric space of non-compact type. We can visualize it in the ball model. Okay, and we can compactify this space by considering equivalence classes of non-divergent geodesics in this space. Okay, and these equivalence classes give rise to the ideal boundary, which here is represented by M infinity. And topologically, this is a sphere. And okay, so we can extend the action of G to this ideal boundary, and we can talk about stabilizers. Okay, so this is the geometric definition, but I'm not interested in that. I'm interested in the algebraic description of these subalgebras. So this will need a lot of notation. Let us try to explain this. So the construction of a parabolic subalgebra depends on a choice of a subset phi of simple roots. Recall, pi was the set of simple roots associated to the symmetric space or to G. Okay, so we choose phi. Okay, here we have the picture I showed you before. Okay, so a particular choice could be this one. I choose these three nodes here, these three simple roots, and this other one. Good. Now let me denote by delta phi and delta phi plus the roots, positive or not necessarily positive, spanned by phi. Okay, this would be the yellow roots in here. Recall that each node represented a root. Okay, and now we are going to define subalgebras of G associated to these roots. Okay, so the first one, I will call it L phi. So L phi is G naught plus the G alphas. If I add all the G alphas, I recover G, but I am not doing that. I'm only considering the roots spanned by phi. Okay, so in the picture, I can visualize this as adding the root spaces in yellow and then G naught, and G naught is represented by the yellow rectangle here. Okay, and now I define this other nilpotent subalgebra, N phi. This N phi is the sum of the root spaces whose roots are not spanned by phi and are positive. So positive means in the picture above in the triangular above the rectangle. Okay, And not spanned by phi means not yellow. So these are the roots in here. Okay. Good. The green nodes are there. We also define this abelian subalgebra as the intersection of kernels of elements in phi. I will need this later. But in order to define the parabolic subalgebra, we by the way, we can represent it in this way in the picture. Okay. And in order to define the parabolic subalgebra, we just need to sum L phi and N phi. Okay. So this construction depends on the choice of phi as a subset of simple roots. Notice that if we take a bigger subset of simple roots, psi, then the corresponding subalgebras respect these inclusions. For instance, if we add this other green node to the set of simple roots, then we get something bigger. Okay. So I copy here these definitions, and I still need one more definition, which is this subalgebra of G generated by the root spaces associated to roots spanned by phi. Okay, so this is basically the same as L phi, but without this A phi part. Okay, roughly speaking. Good. And now we can talk a little bit about geometry. So let me consider the connected subgroup S phi of G with this Lie algebra. Okay, and if we consider its action on M, then the orbit through the origin turns out to have some nice properties. This is called a boundary component or a boundary symmetric space associated to phi. It is a totally geodesic submanifold, and therefore it's a symmetric space itself. In this case, of non-compact type, so it doesn't have abelian factors. Its rank is the cardinality of phi, and the isometry group, the connected component of the isometry group, is up to covariance S phi. Okay, so B phi is S phi mod the isotropy. Okay, good. Now, there is a classical result, the horospherical decomposition, that tells you that M is diffeomorphic to this product, N phi times B phi, and A phi and N phi are the connected subgroups of G with the corresponding Lie algebras. But we can regard this result or restate this result in a different way. Okay, let us consider the group A phi and phi. Okay, this is a Lie subgroup of G. It acts isometrically on M, and it turns out that this action is free. It's polar, okay, and polar means that there is a submanifold of M intersecting all these the orbits of this action, and always perpendicularly. Okay, and this submanifold is called a section. In this case, the section is B phi. Okay, recall that B phi was totally geodesic. In this case, each orbit intersects the section only once. And moreover, all orbits are mutually congruent and minimal, zero constant mean curvature. Okay? This is important, all this information is important, and it's related to one of the methods that I mentioned some minutes ago, called the canonical extension. So geometrically speaking, this means the following. Here I represented by these lines the orbits of the action of A phi and phi. And here in blue, I think, you have the section, B phi. Okay, now imagine that on B phi you have a submanifold or an action, okay, a homogeneity one action with some orbits. Imagine that this is one of the orbits. Now you extend this orbit to a bigger submanifold of the ambient space by attaching all the A phi and phi orbits. Okay, you do something as in here. If you do this with all the orbits of a homogeneity one action on B phi, you get a foliation, singular foliation on the ambient space on M, and it turns out that this foliation is homogeneous. Okay, so you can extend actions. In the next slide, I will explain this method more formally. Okay, but geometrically speaking, this is how it works. Okay, so let's come back to the situation we had. We had a group H acting with cohomogeneity 1 and a singular orbit. We were under this case on M. Okay, and its Lie algebra was assumed to be contained in a maximal proper subalgebra Q of this form. Okay, where QEL was maximal parabolic in GL. This was the case that was remaining. This implies directly that Q itself is maximal parabolic in G. Okay, and therefore, by the description of the parabolic subalgebras, this Q is of this type up to conjugacy. Is Q phi with phi maximal proper in pi. This means that it is pi minus some simple root alpha. Okay. So it was proved almost 10 years ago by Berndt and Tamaru that in this case, in this situation, then the H action is orbit equivalent to a canonical extension or to a nilpotent construction. And I will quickly explain these methods. So the simplest one, the canonical extension. In order to canonically extend an action, what you need is precisely an action, say of a group H phi, on this boundary component, recall, on this smaller symmetric space that lives totally geodesically inside our big symmetric space. So we are giving a cohomogeneity 1 action here. Now we simply attach the Lie group A phi and phi. This turns out to be a Lie subgroup of G, and it acts with cohomogeneity 1 on the big space. This is the canonical extension. Okay, so you need to give me phi, set of simple roots, and a group acting with cohomogeneity 1 on a lower rank space. Okay. Now let's go for the nilpotent construction, and this is very the most difficult method to understand. I will go very quickly over it. So this construction depends on a grading of this n phi. This grading depends on the choice of this alpha that we are removing here. Okay. Now it depends on the choice of a subspace V of the first space of this direct sum. Okay. Now, if these two technical conditions are satisfied, okay, forget them for a second, then the Lie group with this Lie algebra acts with cohomogeneity 1 on M. So this provides a method to construct cohomogeneity 1 action. So let's look at the Lie algebra of the group here. So you have n phi, the orthogonal complement of this V in n phi, and here you have the normalizer of this set. So this turns out to be a Lie subalgebra. And what these two technical conditions mean is that this V is the normal space to the singular orbit of this action, okay? And they are requiring not only this, but also that the slice representation at this singular orbit is transitive on the unit sphere of the normal space, okay? So this is how these two conditions are, in a way, it's a way to restate this, okay? But this turns out to be difficult to determine precisely the subspaces V that satisfy these two conditions. This is rather difficult, okay? Even in the rank 1 case, it was very difficult to solve this, to determine all these subspaces, okay? But at least the method is more or less clear. Good. So here I would like to summarize the fundamental things that I have told you so far and explain the remaining arguments. Okay, and in the last slides, I will tell you very quickly how to apply this result to some particular cases. So we have these two possibilities. If you don't have a singular orbit, then we know a complete classification. We have two types, solvable type or spherical type. Difficult case, when you have a singular orbit, then the Lie algebra can be contained in this this type of maximal proper subalgebras or this one. Okay, in the first situation, then what you get is a diagonal action on a product of two rank 1 homothetic symmetric spaces. So the cohomogeneity 1 action is determined by such a diagonal action. Say this is well understood. Okay, so we go for the other case. Then we distinguish two cases, QL reductive or parabolic. If it's reductive, then the homogeneity one action has a totally geodesic singular orbit on one irreducible factor, and these actions had been classified. So we understand this. And in the parabolic case, this is a maximal proper parabolic subalgebra, so it is determined by a choice of simple roots phi. Okay, and in this situation, the result of Berndt and Tamaru tells us that the action is constructed by nilpotent construction or canonical extension. Okay, now imagine that the action precisely is constructed by canonical extension. So this means that it's obtained by extending an action on a lower rank symmetric space. So what you have to do, this suggests a recursion here. So what you have to do is to go back to this situation, changing M by the lower rank symmetric space, this boundary component, B phi, and therefore pi by the new set of simple roots, which now will be phi. Okay, and do the process again. You may end up again in canonical extension, and then you do it again. Okay, so at the end of the day, since you are decreasing rank, you cannot at some point you cannot have any more canonical extension. Okay, so what you have to do is in these three possibilities add canonical extension of what we had before. Okay, more precisely, canonical extension of a diagonal action on a reducible boundary component of this type. Canonical extension of an action with a totally geodesic singular orbit on an irreducible boundary component. And in this case, canonical extension of an nilpotent construction. But one of the technical lemmas of our work is to show that a canonical extension of a nilpotent construction is indeed a nilpotent construction. So here we can simply say nilpotent construction. So forgetting about canonical extension, these were the 5 possibilities in our main theorem. Okay.
Can I ask a question?
Yes.
Maybe, sorry if you were going to talk about it anyway, but so when we talked about this diagonal action where the result of Dynkin was that this maximal proper subalgebra must be like the diagonal bit of this G, J, and plus G, K, and then we somehow deduced this, that both of them must correspond to rank 1 symmetric spaces. How did it happen again?
Why did it happen?
Yeah. So why? So it's
because
clear why they must be isometric, but why must they be of rank 1?
Yes, because this diagonal action that you mentioned has a homogeneity, the rank of each one of the factors. This is standard. This is a dual of a Hermann action, and this is easy to prove. Okay. And therefore, you have a homogeneity one action. It must have rank 1.
Okay. Thank you.
So these were the examples in the possibilities in our main theorem. Let's see how to apply this to this family of symmetric spaces. SLN plus 1 over SON. This space has rank n. Its Dynkin diagram has this form here. Okay, so let's go through the 5 possibilities. Solvable type, we understand it very well. Horospherical type as well. And now we have the canonical extensions from reducible boundary components or from irreducible boundary components. Okay, so we get this list. Okay, so when we describe a canonical extension, we must give the boundary component from where we extend and the action that we are extending. So it will be the action of this H phi. For instance, in the case of canonical extension of a diagonal action, in this situation, these reducible boundary components of rank 1 correspond to taking 2 non-consecutive nodes in the Dynkin diagram. And this boundary component must be necessarily a product of 2 hyperbolic planes. Okay, and the action is the diagonal action of the isometry group of one of these planes, SL2R. Okay. In the case of canonical extension from an irreducible boundary component, this means that the phi determining the boundary component is a connected set of simple roots, a connected set of nodes in the diagram. Okay, if this connected set just has one element, then the boundary component has rank 1. It's a hyperbolic plane. And as I said at the beginning of the talk, the only action with a singular orbit on a plane, on a hyperbolic plane, is up to orbit equivalence, the action of SO2. Okay, so this is one possibility. And for higher rank, you get these other two possibilities. Okay, and for this, you look at Berndt and Tamaru's list. Okay. And finally, one has to look at nilpotent construction, and this is another difficult part. Okay, but in this case, one can do it, and one gets examples. But it turns out that the examples we get are up to orbit equivalence, the same as these canonical extensions. Okay, so this allows us to get a complete list of cohomogeneity 1 actions on these spaces. And finally, what happens with reducible spaces? Imagine that M is a reducible symmetric space. Therefore, a product of other symmetric, irreducible symmetric spaces, M1 up to MS of a non-compact type. Okay, so whenever you have a product, you can construct cohomogeneity 1 actions by taking a cohomogeneity 1 action on one factor and then adding the isometry group on the remaining factors. This is what we call a product action. Okay, so it turns out that actions of solvable type, these canonical extensions from irreducible boundary components, and more importantly, because this is in general difficult, the nilpotent constructions, all these three possibilities yield product actions. Okay, so this means that we can reduce this study of cohomogeneity 1 actions in here to the study of cohomogeneity 1 actions on each factor. Okay, and recall that horospherical type actions and these canonical extensions from reducible boundary components were well understood. Okay. So in particular, one could apply this to classify cohomogeneity 1 actions on products of hyperbolic spaces, because in hyperbolic spaces, we know a complete classification. So I'll finish here. I leave you here with the sketch of the proof, and I'm finished here. Thank you very much.
Thank you very much for a really interesting talk. Are there questions? I have a question. I was wondering if you could just kind of go back over the nilpotent construction. I think I missed some of the notation on that.
Yes.
So what is L sub phi here?
L sub phi. Yeah, this I defined previously. This is a reductive subalgebra. Let me go back just in case. Okay, I don't know if you can see it here in the second line. L sub phi is
okay.
It's somehow you consider the whole root decomposition, but in here you don't add all the root spaces, but only those corresponding to phi. Okay.
Oh, okay.
Okay,
yeah.
so this L phi somehow the isometry group of the B phi times an abelian factor, or times a flat factor, something like in this here. Okay, so yeah.
I see. So L phi is the corresponding Lie group here.
Sorry?
So L phi is the corresponding Lie group.
Yes. The L phi, capital L phi is the corresponding Lie group. Here in the last line, I should say the connected group with this Lie algebra. Yes. So these are transitivity properties. The first one, okay, this L phi, of course, acts transitively on the orbit through O. But what we need here is that some normalizer in L phi also acts transitively. This means, in other words, that this L phi O, this orbit, which is totally geodesic, is contained in the singular orbit of the future action, somehow. And the second condition means that you have a slice representation that is transitive on unit spheres, on points of the singular orbit. This is the idea. Okay.
Okay, thank you.
May I ask a question?
Yeah.
So I just wanted to kind of make sure that I got it correctly. This recursive procedure with the canonical extension. So if at some point, if our action comes as a canonical extension from something, we just kind of, because our space initially, this theorem works for the situation where the space is reducible, we kind of just run the procedure again, right? And then we just kind of do it recursively until we arrive to the point where it doesn't come from any canonical extension anymore, and then it's one of the remaining situations. Okay, thank you.
Yeah, exactly.
Are there other questions? Well, if there's no other questions.
There seems to be a question in the chat.
Oh, I'm sorry.
In case where you have a singular totally geodesic orbit, can you say something about the normal holonomy? No, I don't know enough about this. I'm not sure this is so simple, because even in the complex hyperbolic space, I'm not sure.
Okay. Sorry, Miguel.
Yeah.
Again, terrible sorry about the stupid question.
No, it's no, it's very natural, but yeah, I don't know enough to answer it.
Okay, thank you.
Any other questions? Thank you again for a really nice talk.
Thank you very much for the invitation. Yeah, and for hearing it.
And the next time we'll meet will be in 2 weeks. It'll be with Jeffrey Streets. So thank you.
Yeah, so thank you.